Assalamu alaikum. So inshallah today we'll continue our talk in chapter 1, Introduction to Thermodynamics in lecture. We spoke last time about introduction to thermodynamics. We started in the first lecture with some definition, and we talked about the English and standard system of unit and also the dimension. In the second lecture we spoke, we got little in deep, we defined the difference between the different system actually of thermodynamic, open system, closed system. And also we have moved to some other basic definition and also the definition of cycle and process and the difference between them, and also the definition of a steady state process. Also we have defined also the temperature and the different temperature scales that are being actually used. We have considered actually the SI system for temperature measurement in terms of Celsius and Kelvin scales, and also we do have in the English system of unit we do have the Fahrenheit and the Rankine scale, and we have introduced to the basic concept of temperature measurement of all of these scales. Today inshallah we'll continue our talk about the pressure and also the pressure measurement and the different pressure scales. So this is for today. We'll be talking about pressure. So let's say we do have actually a body. Let's say we do have a rigid body, something like this, and this body actually is being subjected to a force inclined a certain angle, let's say theta, in x direction. So if we just decompose actually this force, so we'll have actually normal force, normal to this body actually and to inside, and we do have actually another force which is called the tangential force. This tangential force actually causes what's called actually the shear stress, which is equal to the tangential force divided by area, and also it is calculated in Newton per meter square. This normal force, which is normal to the body, to the inside of this body, not to outside. This normal force actually is called actually as the pressure force, which is equal to actually this normal force, causes what's called actually the pressure, and it is equal to actually the normal force divided by the area, and this pressure is calculated in Pascal. So the tangential force on a system causes what's called a shear stress, but the normal force is the force that causes the pressure, and this pressure force is normal to the body and to inside of this body. We do have actually different pressure scales. As we said last time, while we are talking about the temperature, we said actually to have any scale, you can make actually your own scale, but for any scale actually you have to have a reference point. Here also in the pressure scale we have actually different scale with different reference point. We do have what's called the absolute pressure, and we do have also what's called the gauge pressure scale, and we do have also the vacuum pressure scale. The absolute pressure scale actually calculates the pressure in reference to actually the absolute vacuum pressure, which is equal to actually zero pressure. We cannot have a pressure less than the absolute vacuum pressure, and we cannot have actually a value of negative pressure. So usually pressure is a positive value, even when we do have a vacuum pressure, because vacuum pressure is actually considered as a vacuum pressure and as negative pressure in some cases because it is actually less than the atmospheric pressure. However, this value is a positive pressure, is greater than zero. But in some cases we should indicate some referencing are actually indicating this vacuum pressure as a negative value, but this is actually with respect to the atmospheric pressure. We have the atmospheric pressure is equal to around 100 kilopascal, so it is not equal to zero anymore. So also you have to keep in mind that we cannot have negative pressure, or we cannot have actually in our nature a pressure less than absolute vacuum. So the absolute pressure scale measures the pressure in respect to the absolute vacuum, and we do have also two other scales, the gauge pressure and the vacuum pressure scales. They measure actually the pressure with respect to the atmospheric pressure. So the reference point here for the gauge pressure is the atmospheric pressure, and also for the vacuum pressure the reference point is for measuring the pressure is the atmospheric pressure. In case of gauge pressure, when the pressure, absolute pressure, is greater than atmospheric, we call the difference between atmospheric pressure and absolute pressure as the gauge pressure. If the absolute pressure is less than atmospheric pressure, so we call this difference between atmospheric and absolute pressure as a vacuum pressure. So let's look here. If we do have actually this reference line, we call this line as actually representing, let's say, the atmospheric pressure. And this baseline representing the absolute vacuum pressure when the pressure actually has the lowest value, which is equal to 0 absolute pressure. If the pressure, if we do have pressure, the absolute pressure is greater than actually the atmospheric pressure. So if this value is greater than the atmospheric pressure, we call this difference actually between atmospheric and absolute pressure as the gauge pressure. So if we do have pressure absolute, the absolute pressure is greater than the atmospheric pressure. In this case, we call actually the difference as the gauge pressure. So in this case, the definition of the gauge pressure is equal to the difference between B absolute minus B atmosphere. Usually the atmospheric pressure, so let's have an indication about this value. This value is equal to almost 1 bar or 1 point B atmosphere is equal to around 1.10235 bar, which is almost actually around 100 kilopascal. So you have to keep actually this value in mind. If it is not given in any problem, you have to substitute the atmospheric pressure equal to almost 1 bar, which is equal to actually around 100 kilopascal. Exactly actually this value is equal to 101.325 Pascal. Okay, so this is the value of the atmospheric pressure, but usually we keep it in mind if it is not given as 100 kilopascal. So if the absolute pressure is greater than atmospheric pressure, we call this difference between absolute pressure and atmospheric pressure as gauge pressure. And this is actually the definition of the gauge pressure equal to B absolute minus B atmospheric. If we do have actually this pressure, let's consider this line as red line. Right, and this line, if we do have the absolute pressure is less than the atmospheric pressure, so we call actually this difference as the vacuum pressure. So B vac or B vacuum, if B absolute is less than B atmospheric, so in some cases we call this pressure as the vacuum pressure, and this vacuum pressure is equal to the difference between atmospheric pressure and the absolute pressure. But in all cases, usually you have to keep in mind that pressure is always a positive value. We cannot have actually a negative pressure. Okay. This is actually in terms of the pressure scale. We do have 3 scale. We do have the absolute scale. We would consider actually the reference point as the absolute vacuum pressure, which is 0, B absolute equal to 0. The gauge pressure, which you consider actually the reference point as the atmospheric pressure when the absolute pressure is greater than B atmosphere. We call this difference as the gauge pressure. And we do have vacuum pressure, which you consider also the reference point as the atmospheric pressure, but in this case the absolute pressure is less than the atmospheric pressure, and we call actually this difference as the vacuum pressure. Let's move actually to another topic in slide number 30 and see actually the pressure variation in static fluids, the pressure variation with depths in static fluids. So let's consider the pressure variation with depths in a static fluid. And let's assume actually we do have a fluid, maybe water or something, existing inside a tank. This fluid has a height, let's say h, and actually under atmospheric pressure, so actually the pressure at the top actually of this tank equal to B atmospheric. And we need to know actually the pressure actually at any point inside this point equal to what in terms actually of the fluid properties, in terms of density and the height of the fluid. So let's select a certain point here, This point actually is existing, let's say, at a certain height from the surface of this fluid. Let's consider this one. So this point is existing at a height h from the surface of this fluid. Let's take actually this point and study this point outside. Take this point outside and let's see actually what are the forces acting on this point. So let's consider the 3D representation of this point, of this element, infinitesimal element or something. This element actually has a dimension. Let's say this is delta x. Let's assume actually those are the dimension x, y, and we do have actually the z direction. So this element has the dimension delta x, and it has height actually delta y, and it has actually depth equal to delta z. So it has the dimension delta x, delta y, delta z. This element actually is at rest, so that means actually it is under actually balanced by the forcing acting on this element. So as this element actually is in balance, this means actually the forces, the summation of the forces acting on this element are equal to 0. But let's look at actually the forces acting on this element in the y direction. First of all, we do have the weight acting on this element. Weight of this actually element is equal to what? Equal to mass multiplied by gravitational acceleration. And based on actually Pascal law, pressure is acting actually in all dimensions for a submerged body. So in this case, for the top surface, this surface, let's say, the top surface, we do have a pressure force normal to this surface and to the inside of the body. Let's say the pressure at the top surface is B1 multiplied by the area which should equal to delta Z multiplied by delta Z multiplied by delta X. So we do have pressure is equal to force divided by area. So the force will equal to pressure multiplied by area. So at the top surface we do have a pressure force equal to B1 multiplied by the area. And from the bottom side we do have another pressure force acting upward, normal to the body, to actually upward on the lower surface, which is actually this surface. Okay, this is the lower surface. We do have actually a pressure force acting upward, normal to this surface. Let's say the pressure at the down actually face is equal to V2 multiplied by the area, which is the same as actually delta Z multiplied by delta X. This element actually is at balance at steady state condition, it's not moving. This means actually the summation of the forces in the y direction are equal to 0. So we do have three forces, two pressure forces, and we do have the weight. So in this case we can say we do have the pressure from the top surface P1 multiplied by delta X multiplied by delta Z. This should equal to actually pressure plus the weight force, which is equal to mass multiplied by gravitational acceleration. This should equal to B2 multiplied by delta X multiplied by delta Z. We do have this term, weight is equal to mass multiplied by gravitational acceleration. Mass is density of this actually element multiplied by volume multiplied by gravitational acceleration. So density multiplied by gravitational acceleration, and the volume actually of this element is equal to what? Delta X multiplied by delta Y multiplied by delta Z. So we can just substitute here mg, this term will equal to what? Rho g multiplied by delta X multiplied by delta Y multiplied by delta Z. And based on that we can actually remove delta X, delta Z, delta X, delta Z from this equation, and then we can come up actually that pressure difference through this element B1 minus P2, which is called actually as delta B. The pressure difference through this element is equal to rho g multiplied by del y. Okay? So if we consider actually this is the pressure difference through this element between the top and the bottom surface. But let's consider actually the pressure difference. Let's actually integrate the case for any 2 points actually inside this fluid. Let's say point 1 and point 2. Point 1 has actually height h1 and point 2 have a height, let's say, h2. And we need to calculate actually this pressure difference between those 2 points. So in this case we can consider this integration and integrate actually from pressure P1 at point 1 up to pressure P2, and this integration actually of del y from h1 up to h2, and this is actually should be delta y. So in this case we can calculate actually the pressure difference between any 2 points actually in a static fluid is equal to actually delta B, which is equal to B2 minus B1, will equal to rho G multiplied by rho is the density. We are talking about a static incompressible fluid. Incompressible means the density is constant, gravitational acceleration is constant, so we can take outside. So the integration of delta y from h1 to h2 will equal to rho G multiplied by h2 minus h1, which we call it as actually as delta H. And this is actually the pressure variation between any 2 points within the fluid will equal to actually the pressure difference B2 minus B1 or B1 minus B2 will equal to rho G multiplied by delta H. But let's say we do have actually this point 2 instead actually of B, this is actually B1 minus B2, no, B2 minus B1. It will be H1 minus H2, and we do have actually H1 is greater than H2, so it will be positive. If we consider it actually B1 minus B2, it will be in this case negative, but delta H also will be negative. So yani, it doesn't matter. But if we consider actually point 2 here or point 1 out at the top of the surface, let's consider, sorry, point 2 is existing at the top actually point here or at the surface. The pressure at this point actually is equal to the atmospheric pressure. So the pressure actually of at any submerged point within a static fluid, B, in this case, the pressure will equal to, let's consider B, which is B2 minus B1 is equal to actually in this case B atmosphere. So the pressure at any point will equal to the atmospheric pressure plus rho G multiplied by H. So if we do have any static fluid and we have selected actually any point actually inside this fluid, this point actually, let's say, has a height h. So in this case, the pressure at this point should equal to the pressure at the surface of the tank, which is equal to the atmospheric pressure plus the density of this fluid multiplied by gravitational acceleration multiplied by the height of the fluid. This is actually the weight actually of the fluid column. So the pressure at any point in the static fluid equal to actually the pressure at the top surface plus the weight of the fluid. And this is actually the case. This pressure actually is called as the absolute pressure, because in this case we have considered the value of the atmospheric pressure. If we did not consider the value of the atmospheric pressure and we consider only the weight of the fluid, so in this case actually this pressure is called as the gauge pressure, which is equal to rho G multiplied by H. Because we do have the relation B gauge is equal to B absolute minus B atmospheric. So if we just subtracted B atmospheric from here, then we can get the gauge pressure, which is equal to rho G multiplied by H. For your knowledge, actually, the pressure value in any equation, any thermodynamic equation, should be substituted by the gauge pressure. Except actually in one case, in the ideal gas equation of state, BV is equal to RT. This is the only case that this pressure should be substituted as the absolute pressure. Otherwise, we have to substitute the value of pressure in gauge pressure. So in any equation, we have to consider the gauge pressure value except in the ideal gas equation of state, which in this equation BV equal to RT, this pressure value should be actually the absolute pressure. But if we consider actually a point inside a tank, and this tank actually consists of multiple fluids. So let's consider a tank here. This tank actually consider, let's say we do have 3 fluids. So we do have here fluid number 1, and also we do have here fluid number 2, and we do have here, let's say, fluid number 3, and the pressure at the top of the tank is B atmospheric. And we want actually to measure the pressure at the bottom of this tank, let's say at point 1. Okay? So the pressure at this point will equal to what? B1 will equal to the pressure at the top, as we used to, so this will equal to the pressure B atmospheric plus the weight of the fluid. But in this case, we don't have actually one fluid, we do have 3 different fluids. So fluid number 1 has density rho 1, this one has density rho 2, and this one has density rho 3. And let's say actually the height of the fluid 1 is H1, height of the fluid 2 is H2, and the height of the fluid 3 is H3. So in this case, the weight of the 3 column in this case will equal to rho 1 J multiplied by H1 plus rho 2 J multiplied by H2 plus rho 3 J multiplied by the height of the third fluid, which is actually H3. Okay, so at any point, actually any submerged point in a static fluid, the pressure should equal to the atmospheric pressure plus the column, the weight of the column of the fluid. If we do have different fluids, then we have to consider actually the weight of those different fluids with different height. This pressure is also absolute pressure, because in this case we have considered the value of atmospheric pressure. If we did not consider the value of atmospheric pressure, so in this case this pressure will be presenting the gauge pressure. But in this case we have considered this value, so this means actually this pressure is representing the absolute pressure. Okay. So let's get back to the original equation for pressure variation with depth. Delta B is equal to rho G multiplied by delta H. And see actually this equation. So we said actually delta B is equal to the pressure difference between any 2 points within actually static fluid. Delta B, if we do have here a static fluid, and we do have, let's say, point 1, and we do have point 2. Point 1 have height H1, point 2 have height, let's say, H2. The pressure difference in this case between those 2 points within the same static fluid equal to rho G multiplied by delta H. This equation actually was the basic actually for 2 inventions. One invention actually, the first invention is called actually the hydraulic jack. The idea of the hydraulic jack actually, hydraulic jack like the one actually that you are using actually to raise your car. Just you can apply a small force so that actually you can raise actually a heavy weight or the weight of your car by your hand. So using hand force, so you can raise actually the whole car. The idea of the hydraulic jet actually is that we do have 2 piston cylinder device. One small piston with a small actually cross-sectional area, and we do have actually 1 big piston with actually with a bigger cross-sectional area. So in this case it has actually cross-sectional area A1, and this one has cross-sectional area A2, which is actually much greater than A2 is much greater than A1. The idea here actually based on this equation is that if we do have actually those 2 points, if we do have the heat difference delta H is equal to 0, so this means actually delta B should equal to, delta B in this case also should equal to 0. So this means actually in a static fluid, if we do have 2 points at the same height within the same within the same continuous fluid, so this means actually the pressure heat in this case delta B is equal to 0, because in this case the heat difference is equal to what? Is equal to 0. So for the same actually static continuous fluid, so in this case the pressure at the same height within the same continuous fluid is equal to 0. And this was the idea actually of the hydraulic jack. If you look at actually at a line just below actually those 2 cylinders, this actually space between the 2 cylinders is filled by some kind of oil or something, or any liquid. So if we select actually a point here, let's say this is point 1, and we select another point here, let's say actually this is point 2. If we look at point 1 and point 2, we do have 2 points within actually the same continuous fluid. So this means actually pressure at point 1 is the same as pressure at point 2. So B1 is the same as B2. B1 is equal to what? If we applied actually here a small force on this small piston, F1, this force will be transmitted this oil, and we can generate actually a bigger force on the other piston, F2. Type the pressure at point 1 here is equal to what? Is equal to the small force F1 divided by small area A1, and B2 is equal to pressure, the force F2 divided by the area A2. If we actually got this one, F2 over F1, we can say F2 over F1 is the same as A2 over A1. So F2 over F1 is the same as the ratio of A2 over A1. And we do have actually area A2 is much bigger than the area A1. This means actually that the force F2 generated actually on the bigger piston is much greater than the force actually F1. And this is the idea that actually using your hand, you can just exert a small force on the small piston, then you can generate actually a bigger force, and this actually force is able actually to carry even your car. Okay, so let's look at the slide. In slide 31, here is actually the concept of Pascal law, that if we do have actually 2 points within the same fluid, within the same continuous fluid at the same height, we should have actually those 2 points should have the same pressure. If you look at actually the lower block here, we do have it. If we look actually point A, point B, C, D, E, F, G, all of those points are actually within the same continuous fluid and at the same level. So this means actually their pressure should be the same. But if you look at actually at down, if you see here point H and point I, point H actually is existing inside mercury. We do have mercury. Mercury actually have higher density than water, so it will actually just be down. It will just settle down at the bottom of this tank. So in this case, point H is existing in mercury and point I is existing in water. We do have in this case the 2 points are on the same height and within actually the same tank, but they are not actually within the same fluid. So in this case, the pressure at point H is not the same as actually pressure at point I, because the condition to have the same pressure, we should have the same 2 points at the same level within the same continuous fluid, within the same fluid, not within actually different fluid. And this is actually the concept of Pascal law, and based on actually this concept, we came up actually with the idea of the hydraulic jack. As you can see in the next slide, we can just actually using those 2 pistons, cylinder devices, we can apply small force in piston number 1, then actually we can get bigger force on piston number 2, so that actually we can carry the car. The idea is that the pressure at this point is the same as the pressure at this point, because they are actually at the same height within the same continuous fluid, so they should have the same pressure. And based on that pressure is force over area, then we can see the area ratio is the same as actually as the force ratio. So as you actually make this area ratio a little bigger, this one is little smaller and this one is little bigger, so this means actually also the force F2 will be actually much greater than F1. And this is the idea of the hydraulic jack. Let's consider actually an example in page actually slide number 33. So let's continue with the example number 2 for this chapter. We do have, this is actually slide 33. We do have a piston, vertical piston cylinder device. This piston, we do have a vertical piston cylinder device. This piston actually contains a gas inside. This gas actually is existing at a certain pressure that we don't know. This piston actually is kept in balance, so it is not moving. This piston has mass equal to 60 kilogram, and it has cross-sectional area is equal to 0.04 meter square. And the atmospheric pressure above this piston at a certain actually elevation, this piston is existing, and we do have the atmospheric pressure is equal to 0.97 bars. And we need actually, in this case, and is giving also the gravitational acceleration G is equal to 9.81 meter per second squared. And we need actually to determine actually the pressure within this cylinder. How can we solve actually this problem? He said actually we need to calculate the pressure that can actually keep this piston in position. Keeping this piston in position, this means actually this piston is not moving, so this means the summation of the forces in y direction or in the vertical direction are equal to 0. So let's take actually this piston outside here. So we do have, this is our piston, and look at actually the forces that are acting on this piston in the vertical direction. So first of all, we do have the weight, which is actually mass multiplied by gravitational acceleration, and from actually the bottom of this piston, we do have pressure force. Pressure force is acting through the whole surface and through actually the whole cross-sectional area, equal to pressure multiplied by area. This pressure that we need to calculate. And also from the top of this piston we do have atmospheric pressure, which is also value of pressure. So it is acting on the piston normal to the area and actually to inside of this system. So from downward we do have a pressure force equal to B multiplied by cross-sectional area, the pressure that we need to calculate, and from the top actually we do have the value of the pressure is the atmospheric pressure multiplied by also area. The pressure force is normal to the piston and to inside. The top force will be normal to inside to the piston, and the bottom actually normal on the piston to also inside of this piston. And as actually this piston is at rest, so this means actually the summation of the forces in the y direction, let's say this is y direction, are equal to 0. So this means in this case the pressure force multiplied by area should be in balance with the atmospheric pressure force, B atmospheric multiplied by area, plus the weight of the piston multiplied by gravitational acceleration. We can just divide by area, so this pressure, area will go with area, and then we'll have ME divided by the cross-sectional area. We need to calculate this pressure. Pressure B atmosphere is given here 0.97 bar. So 0.97 bar, we have to convert it actually to SI unit, which is Pascal. So we do have 1 bar is equal to 10 to the power 5 Pascal. So we have to multiply here, we have to multiply by 10 to the power 5 plus mass, which is equal to 60 kilogram, multiplied by gravitational acceleration, which is 9.81, divided by the cross-sectional area, which is 0.04 meter square. If you calculate actually those values, you can see actually that pressure value will equal to 1.12 multiplied actually by 10 to the power 5 Pascal. If we just divide this value by 10 to the power 5, then actually we can get the value of this pressure equal to 1.12 bar, and this is actually the value of the pressure in bar that can actually keep this piston in position without any movement. Okay, he said actually here in this problem, he said as another actually just indicative question, if we do have some heat is actually is transferred to the gas inside this volume, and the volume is double in this case, what do you expect the value of the pressure inside this tank? So we do have, if we do have a kind of fire here or something, so we are heating actually this gas inside, so heat transfer, okay? And this piston is free to move. The piston, he said actually, when actually this piston is moved to a volume which is equal to double actually the initial volume. So in this case, what is the value of the pressure in this case? So in this case actually, as this piston is free to move, so in this case actually the pressure will be remaining the same, the pressure will be kept the same as the initial state. But actually if this piston is fixed, not moving, so in this case actually the volume will be kept constant due to heat transfer, but actually the pressure of the gas will be actually little increased, because the gas by adding heat will try to expand. But if this piston is fixed, so in this case the pressure will increase. If this piston is free to move, this means actually the system will expand, the gas will expand, and actually the pressure in this case will be kept the same. Let's move actually to the next slide. We said the relation for the pressure variation with depth delta B equal to rho G delta H was the basis for two inventions. The first invention, which is called actually the hydraulic jack, we can apply actually a force, a small force, then we can generate actually little bigger force on the second piston so that we can raise actually heavier weight. The second application for this relation, or second invention for this relation rho G equal to delta H, is what's called actually the manometer. Manometer actually is a pressure measuring device. The idea of the manometer actually, we do have here delta B is equal to rho GH. So if we do have actually any 2 points, and we need actually to measure the pressure difference between those 2 points, we do have density is constant, and for incompressible substance density is almost constant, and we do have gravitational acceleration is constant. So this means we do have linear relation between delta B and the pressure heat, which is called delta H. Delta H is called as the pressure heat difference, or the height actually difference between those 2 points. So if actually in some way we can measure the pressure heat difference between the 2 points, so in this case we can multiply by G multiplied by the density, and then we can calculate actually the pressure difference. So let's say we do have actually a flowing fluid inside a pipe or something. So in this case we are not talking about fluid static. We need to measure the pressure for actually a flowing fluid between 2 points. Let's say we do have actually here point 1 and point number 2. So in this case, as the flow is going from 1 to 2, so this means actually the pressure B1 should be greater than what? Should be greater than B2 due to actually the pressure losses and the friction between the flow and the wall. So in this case the pressure should be reduced. So B2 should be less than B1, or B1 should be greater than B2. But if I want actually to measure the pressure difference between those 2 points, point 1 and point number 2. He said in this case actually we can just connect what's called a U-tube manometer. This is actually a manometer. We can have actually 2 openings in this tube, one opening at point 1 and another opening at point number 2. And then actually inside actually this U-tube manometer we can put actually what's called a manometer fluid. Manometer fluid. And this manometer fluid actually has density of manometer fluid should be actually little greater than, or we can consider it actually much greater than the density of the flowing fluid. So this is actually the density of the flowing fluid. If I want to measure the pressure difference between any 2 points, just I will consider a U-tube manometer. Inside this U-tube manometer we do have manometer fluid with a density which is much greater than actually the density of the flowing fluid. Why the density here should be high? Because actually once we open this one, if the pressure difference between point 1 and point 2 is little high, so in this case the flow will be coming inside this U-tube manometer and it will force actually the manometer fluid to go inside the pipe. But this fluid should be little heavier, so actually that it can withstand the difference, the pressure difference between point 1 and point 2. So at a steady state condition, if you made actually those 2 points, you will find actually the pressure, this actually manometer, the fluid inside manometer tube will be raising actually on the other side of the U-tube manometer, and at a steady state actually it will be fixed at a certain height, so that actually we can have height difference here between the 2 surfaces of the manometer fluid equal to, let's say, h. This height difference h should be indicative actually about the pressure difference delta B. But let's consider actually this is point 1 and point 2, and this actually height difference is A, and let's consider actually this height up to point 1 or point 2, let's say actually this height is A, okay? And let's consider actually those 2 points inside this manometer fluid. At the intersection between the manometer fluid and the flowing fluid, I will just actually draw a horizontal line. And let's consider actually this point A, and this point actually on the left hand side of the manometer tube we do have point B. If you look at point A and point B, we do have 2 points at the same height within the same fluid. We can consider actually point A at the intersection of the 2 fluids as being actually inside the manometer fluid, and point B is inside the manometer fluid. So we do have 2 points at the same height within the same continuous fluid. So this means actually the pressure at point A should equal to the pressure at point E. Pressure at point A, we said actually pressure in any static fluid. This fluid inside the U-tube manometer is a static fluid now. So pressure at point A will equal to the pressure at the top, which is V1, pressure at point 1, plus the weight of the fluid. The fluid here actually is actually the flowing fluid with density rho fluid. But what is the height? The height is A plus H. So in this case, rho fluid multiplied by G multiplied by height, which is H plus A. This should equal to pressure at point B. Pressure at point B is equal to what? Pressure at the top, which is pressure B2, plus the weight of the fluid. We do have actually the fluid in this case for height A is actually the flowing fluid. So it is equal to rho fluid G multiplied by A plus the density of the manometer fluid multiplied by G multiplied by H. Less actually rho fluid G multiplied by A will go with rho fluid G multiplied by A. Then we can say the pressure difference between point 1 and point 2, B1 minus B2, will equal to GH multiplied by the difference between manometer fluid, density of the manometer fluid, and the density actually of the flowing fluid. We said the density of the manometer fluid should be much greater than the density of the flowing fluid, so we can neglect actually this value with respect actually to this value, because raw fluid is much greater than the density of the manometer. And based on that, actually we can say B1 minus B2 will equal to rho J multiplied by what? Multiplied by H. And this is actually the idea of the U-tube manometer. We can just make two openings between the 2 points that we want actually to measure the pressure difference between them. Bottom manometer fluid with a density little higher or much higher actually the density of the flowing fluid. At a steady state actually we do have higher difference. The pressure difference B1 minus B2 is equal to rho J multiplied by rho of the manometer fluid, not the flowing fluid. The density of the manometer fluid multiplied by gravitational acceleration multiplied by H. But if actually I want to measure the pressure at a given point 1, not actually pressure difference between point 1 and point 2. So in this case, just we can make U-tube manometer, but the other end, actually the left-hand side end, is just open to the atmosphere. So instead of B2, it will be B atmosphere. So in this case, let's say we do have a gas inside the tank. We do have a gas, and this gas existing at a certain pressure, and we want actually to measure this pressure. Again, we can make actually a U-tube manometer. Inside this U-tube manometer, we'll have a manometer fluid. Based on this pressure, we can make this opening. We'll have actually a height difference, let's say H. And again, at the top here, we do have the pressure is atmospheric pressure. So if we consider those 2 points within the same fluid, point A and point B, and then you can apply pressure at this point is the weight of the fluid plus this P, weight of the fluid which is gas, which is neglected, so it will equal to pressure B. So the pressure B in this case will equal to the pressure at this point, which is equal to the pressure at the top, which is atmospheric pressure plus density of the manometer fluid multiplied by J multiplied by H. In this case, this pressure is calculated in absolute value because we have considered the value of the atmospheric pressure. And in this case, the gauge value, just subtract atmospheric, which is rho manometer fluid multiplied by J multiplied by H. So the absolute value is equal to B atmospheric plus rho GH. The gauge value, just to subtract B atmospheric, will equal to rho manometer fluid, rho of the manometer fluid, multiplied by gravitational acceleration, multiplied by the height H. Okay? And this actually one of the pressure measuring devices, which is called the manometer, the U-tube manometer. There are actually some other pressure measuring devices which we can just introduce here. If you look actually at the next slide, we do have what's called the Bourdon tube. The Bourdon tube actually can have actually different shapes, maybe C shape or spiral shape, or actually it may have actually the twisted tube shape, or it may have also the helical shape. The idea actually of the Bourdon tube is that we do have, let's consider the helical shape. We do have actually a tube with 2 ends. One end actually is fixed, and the other end actually is free to move. This fixed end actually, fixed open end, which is actually is subjected to the pressure that we want actually to measure. Okay? And actually the free end is closed end, and this is actually connected to a kind of pointer, and this pointer actually we do have is connected to a scale here, is calibrated to a scale to have the reading of the pressure. The idea is that actually when we subject this device to a pressure B, the flow here at this pressure will just get into actually this spiral tube. So what will happen in this case? This end is open and this end is closed. So the flow will get actually inside, and depending on this pressure actually the free end will try to deflect with a certain angle. This deflection actually is calibrated so that actually we can read the pressure value on this scale. So depending on the pressure, the flow will get inside, and this free end actually due to pressure will just be twisted with a certain angle. So based on this twisted angle actually we can read the value of the pressure, and this scale actually is being calibrated. Also we do have what's called the pressure transducer. The idea of the pressure transducer is that actually we do have a material. This material actually with variable resistance, so when it is actually subjected to the pressure, so this resistance actually will be valid. So in this case actually we can connect this actually to an electric cycle. So we can apply here a fixed amount of current. So the current is fixed and we know actually this value. And this resistance will be function of the pressure. So this resistance is function of the pressure. This resistance varies actually depending on the value of the pressure. And then actually based on this actually circuit, we can actually measure the volt here, which is equal to the current that we know its value. And this resistance is function of pressure. So depending on the value actually of the volt, we can actually calibrate the system to read directly the value of the pressure. And this is the idea of the pressure transducer. We do have also another pressure measuring device, which is called actually the strain gauge pressure transducer. A strain gauge pressure transducer, the idea is that we do have a diaphragm, is separating actually two chambers. One chamber is actually, the top one is subjected to atmospheric pressure, and actually the bottom one is subjected to the pressure that we want to measure. And this actually red line represents the diaphragm. The diaphragm actually is a material, is an elastic material. It is actually, it accepts actually to be expanded or contracted depending on the pressure. So if we do have a pressure here, this pressure actually depending on this value of pressure, we should have actually a deflection angle of this diaphragm. So this diaphragm actually just will be deflected. This diaphragm is just connected here to a pointer. So, and also this pointer is connected to a scale so that actually it can read the value of the pressure. So depending on the pressure, this diaphragm will be deflected, and then actually based on that actually this pointer will be raised to read actually a certain value of pressure. This is actually what's called the strain gauge pressure transducer. We do have also piezoelectric pressure transducer. In this case actually we do have a special kind actually of crystalline structure material, in which actually we do have, once this material is subjected to pressure, some electric current is generated within the system depending on this pressure. And this substance, this crystalline structure material has actually fixed resistance in this case. So the same we can connect it to an electric circuit, but in this case we do have current coming out from this crystalline structure material. Based on the resistance, then we can calculate the volt. This volt value should be calibrated to read the value of the pressure. Most of these actually pressure measuring devices are calibrated actually to read what's called the gauge pressure, because as you see here, we do have the pressure in this chamber is B atmosphere and the pressure here is P. If pressure is equal to B atmospheric, this diaphragm will not be deflected anymore. So the pressure reading here will be equal to 0, indicating if the gauge pressure is equal to 0, this indicates actually that the pressure is equal to the atmospheric pressure. So all of these devices are used actually to measure pressure that is actually higher or lower than the atmospheric pressure. But what if we need to measure the atmospheric pressure itself? So let's look at actually the next slide. If we want actually to measure the atmospheric pressure, we do have a device which is called the barometer. The idea of the barometer is that we do have mercury. We fill actually a glass with mercury, and we do have also a tube. We fill actually also this tube with mercury. This tube actually has open end, and just take this tube and just flip it down inside actually this glass of mercury. So just we will fill this tube with mercury and fill it down. So at steady state condition, you will find actually the mercury level inside this tube will be actually stopping at a certain height, this height h, which balance actually the atmospheric pressure, and some actually mist here or vapor of mercury will be created in this free zone. So if you consider here, this is actually the tube. If we consider here 2 points, 1 point inside this tube and 1 point outside this tube, so point 1 and point 2. Point 1 and point 2 we do have the same fluid, which is mercury, at the same height. So this means the pressure P1 is the same as B2. Pressure B2 is equal to what? At the surface of the mercury. This actually is the atmospheric pressure. So we can say atmospheric pressure will equal to the pressure at B1, which is equal to the pressure at the top, B vapor, which is very low value. Some mist just created, so we can neglect this value, plus rho of the mercury multiplied by gravitational acceleration multiplied by the height h. This value is neglected. So the atmospheric pressure is equal to rho mercury g multiplied by h. If you did actually this experiment, you will find actually this height h is around actually 76 centimeter, around actually 750 millimeter or 76 centimeter. So we do have the density of mercury is around 13,600 or 595 multiplied by gravitational acceleration, which is 9.81, multiplied by this height 76 centimeter, which is 0.76 meter. If you calculate actually those values, multiply together, you will find the value of the atmospheric pressure is equal to 101,325 Pascal, or it will equal to 1.01325 bar. Just if we divide by 10 to the power 5, this will be actually the value of the atmospheric pressure. So if in some problem he said actually we have actually made the test to calculate the atmospheric pressure at a certain height. So usually actually this height of mercury is depending on actually at which altitude we are measuring the pressure, because as you know, while actually going up in the atmosphere, the atmospheric pressure will be getting down. So if we are measuring the atmospheric pressure at the top of mountain or something, you should find actually this value is less than 76. So he can tell you actually this value at this position. He will say actually, let's say we do have the height equal to, let's say 60 centimeter. Let's calculate actually the atmospheric pressure. So in this case, the atmospheric pressure will equal to the density of mercury, which is this value. It should be provided, multiplied by G, multiplied by actually this height. Then we can calculate actually this pressure in Pascal. If you just divide actually this by 10 to the power 5, then we can get this value in bar. And this is actually what's called the atmospheric pressure. Here in the next slide, in the last slide, you can see actually this is an example. You can just go through this example. In this example, we do have, in some cases, if the pressure is high, we said if I want to measure the pressure of a gas or something in a tank, then we can consider a U-tube manometer. And inside this U-tube manometer, we put a manometer fluid and then we measure H to measure this pressure. But in some cases, if the pressure is very high inside actually this tank, so in this case, this means actually 1 manometer fluid should not be able actually to withstand this pressure. So in this case, we can add actually another manometer fluid. The idea actually of solving actually any of this problem, you have to look at actually the intersection point between the flow and the manometer fluid. Just draw a horizontal line, and then actually you can say the pressure at the same height within the same fluid is the same, and then we can generate the equation, and then based on that we can calculate the value of the pressure. Just to go through this example actually as a practice, and actually that's it for this chapter. The last thing actually for this chapter is the problem solving technique. If you do have actually any problem, I will actually read clearly the problem statement and just draw a schematic diagram like what we are doing here, just draw a certain schematic representing actually this problem, trying to understand this problem, and then make the assumption if actually gravitational acceleration is not given, so we have to provide this value, it's almost fixed. And also if we don't have, if in some problem like the example number 2, the atmospheric pressure was given, but if it is not given, so in this case we can assume the value of atmospheric pressure. So any missing variable we can actually give an approximation, and we can give actually an approximate assumption. Then we can apply the law like Pascal law, which says the pressure within the same continuous fluid is the same at the same height. This is actually a law. Then actually we can apply this law so that we can generate an equation, and then based on that we can calculate the pressure. Then we have to know about the properties. We need to calculate here, to calculate atmospheric pressure, we need to know about the density of the mercury in this case. This is actually one property of this mercury. So we have to calculate to know about the properties, get the properties, and then do the calculation, and then actually we can get the final result. After getting the final result, you have actually to reasoning actually this value. See, actually check this value is logical value or not. So if you calculated the atmospheric pressure and you found actually this value instead of 1 bar is equal to, let's say, 100 bar. So something actually should be wrong with this value. Okay? Atmospheric pressure cannot be 100 bar. Okay, so in this case you have to check actually again your calculation. And this is actually a systematic problem solving technique. By this actually we are done with the first chapter of thermodynamic introduction. So inshallah we'll see you in chapter 2 and the first lecture of chapter 2. Thank you.